Okay, here we're going to learn how to find the area between two curves. Okay, well, actually you could do two or more curves, but we just would limit ourselves to just this. So as an example, let's do a kind of problem that you've seen before where you wanted to calculate the area bounded between a curve and the horizontal axis, in this case, the x-axis. So let's suppose that we had the basic squaring function shifted upwards 2 units. And this is not to scale, which is okay. So the area we want to calculate is right here. Okay. So now if you remember, gang, when you did this before, you want to set up an integral that represents this area. And if we go through the steps just as a reminder, it's not going to hurt. The way that we would do this is we would take a number or some point between 0 and 4, say maybe here. Okay. And corresponding to that x hash mark is that very thin rectangle right there. Remember, we referred to this in an earlier presentation when we discussed differentials, right? We called this very, very thin rectangle a differential element of area. It touches the curve here. Okay. Now the area of that differential element, we call it dA, not capital A for area, but the differential of A. Remember, differential means a very, very tiny amount. So here, because it's a thin rectangle, the area of this rectangle is going to be the length times the width. Now the length is given by the height of the rectangle, in other words, the y coordinate. And then we multiply that by the width of the rectangle, the horizontal width, right, which would be this, very, very thin. We called that dx. Okay. And then to calculate the area of the entire region, we say that the total area is equal to the sum of all of those individual elements. Do you remember that? That the integral symbol is really the letter S, which means sum. So you want to sum up all those individual elements. And there's an infinite amount of those elements in there. And all of those elements range from x equals 0 to x equals 4. All those elements are represented by this expression. After that, it's just straightforward integration. But what about if there were two curves? Okay, let's suppose, gang, let's suppose that we had the basic square root function. Okay, and let's suppose underneath of that, we have the basic squaring function. And the area trapped between those two curves would be this right here. And we would like to calculate the area of that region. Okay, now it's very common, kids, it's very common that when we want to find the area trapped between two curves, the intersection points are going to be necessary for us to find because they often wind up being the limits of the integration itself. Now, we know that one of the intersection points is right here at x is equal to 0. The other one I think we can get by inspection. Where do they meet up again? Yeah, good. They meet up again at x is equal to 1. Okay. All right, now, how can we get the area between those two curves? Well, one thing we can do is we can find the area underneath the basic square root function first. Okay, what area would be underneath the basic square root function? Let me use a different color. Okay, the area under the basic square root function would be this much. right? It would be all this right here. And that would be the integral that represents it. But the next, maybe what we would do next is we would take the area underneath of y equals x squared, the basic squaring function. All of this right here. And subtract it out. Oops. Okay. Notice, though, that you can actually combine those under one integral symbol. Okay. That's the idea behind all sections in calculus where we want to calculate the areas between curves. Okay. All right, so let's do this though, gang. Let's do this with the use of differentials, the way we've discussed with the example above. Okay, so let me start this again. All right, so that's our basic square root function, and then the basic squaring function will come up like this. Okay. Notice that the region trapped between these ranges from 0 to 1 along the x-axis. So what I'll do is, similar to what we did in the example above, I'm going to figure out a value or a hash mark for x, say maybe right here. And the differential element of area, remember the very thin rectangle that corresponds to that hash mark is right here. Okay, see it? Now what I'm going to do is I'm going to label the top and the bottom of the rectangle. So down here, the bottom of the rectangle touches the basic squaring function at this point. The top of the rectangle touches the basic square root function at this point. So the area of that very thin rectangle is going to be the length of the rectangle. Now, how would you find that? How do you find the length of the rectangle? Well, you know what it is, kids. Look, it's this vertical length right here. And that vertical length can be found by taking the difference of the y coordinates, the top and the bottom of the rectangle. Okay, the vertical length of the differential element can be found by taking the difference of the y coordinates. And so here, that's going to be the square root of x minus x squared. That's the length of the rectangle. And then we multiply that by the width of the rectangle. Now that's just one, right? Theoretically, there's an infinite amount of those rectangles that make up the entire shaded region. So we say then that the total area is equal to the sum of all of those elements as they range from x equals 0 to x equals 1. And all of those elements are given by the expression square root of x minus x squared dx. Now, once you get to that step, it's a routine integral. Okay, it's a routine integral. You can integrate both of those term by term and use the fundamental theorem. Okay, I'll leave that one to you. That's a nice one. Okay, let's try the next example. How about we say we want the area. This is going to be the basic sine function from 0 to pi. Okay. And then we want to calculate the area trapped between the basic sine function and, let's say, the basic cosine function, which would look like this. Just this wedge. Okay, I want to find just that wedge of the area trapped between the cosine and the sine. All right, now I'm going to need, I see that the region begins at the origin, x equals 0, but where does it end? So this intersection point right here, we're going to have to figure out what that is. Remember, we said this a few minutes ago, right? It's often that the limits of integration for the area between two curves winds up being the intersection points, one or both. Okay, so in this case, we're going to have to figure out, because the region ends right there at that dot. Now we can find that. We could probably just use our knowledge of trigonometry in the unit circle. Where is the sine and the cosine the same? Yeah, quadrant 1. What's the angle that makes them the same? Good, 45 degrees or pi over 4. Now, if you didn't remember that right away, what you want to do to find the intersection points between two curves, or the intersection points of two curves, you force the two functions equal to each other like this, and then solve the resulting equation for x. So for example, in this case, if I divide out the cosine, well, first of all, the equation says, where is the sine equal to the cosine? An exercise that we just did a minute ago, okay? Alternatively, you can divide both sides by the cosine to get the tangent of x is equal to 1. You could proceed that way. All right, let's see. But to continue with what we're working on here, so now between 0 and pi over 4, I'll choose a generic x, say here, and the corresponding rectangle that corresponds to it is right there. Now I'm going to label the top and the bottom of the rectangle like we did in the previous example. That's just good practice, okay? So here, that's going to be x cosine x. And then the bottom of the rectangle is going to be x sine x. Now to calculate the area between them, the differential element of the area is equal to the length of the rectangle, which we said is the difference of the y coordinates. So in this case, it's going to be the cosine minus the sine. Times the width of the rectangle, which is dx. The sum of all such rectangles that make up the entire region is the sum of all of those individual elements, as those elements range from x equals 0 to x equals pi, and all elements in this case are given by the expression cosine minus the sine. And again, it's just going to be a routine integration problem. Maybe this one, we'll go ahead and carry this one out. We can read them off term by term. Right, so here we're using the fundamental theorem. Okay, and so we input the sine, we input pi first, right, pi. So we're going to have the sine of pi plus the cosine of pi. And then minus the sine of 0 plus the cosine of 0. And then we simplify. All right, let's see. Sine of pi is equal to 0, so the first one drops out. Cosine of pi is -1. Oh, I'm sorry, gang, pi over 4. Pi over 4. I got ahead of myself. Pi over 4. So let me clean this up a little bit here because I got a little overzealous. Get rid of that. Get rid of these. And let's put it the way it's supposed to be. Pi over 4, pi over 4. Okay. So the sine of pi over 4 is square root of 2 over 2. So is the cosine. The sine of 0 is 0, so that's out. And the cosine of 0 is equal to 1. So it looks like we'll have 2 root 2 over 2 minus 1 for the total exact area between the two curves from 0 to pi over 4. Okay, so let's do this. Let's say in general, if we've got two functions, let's say f of x and g of x, where one is, we'll say, higher than the other. So let's say that this is f of x right here, y equals f of x. And then underneath of that, we've got y equals g of x. And we'll say that they are bounded between a and b. Here's the area trapped between them. If I add a differential element of area, say right about here, okay, there's my very, very thin rectangle. Label the top and the bottom of the rectangle. Okay, so this one will be x f of x. And this one down here will be x g of x. Okay, then the area of that one rectangle, so the length of the rectangle can be found by taking the difference of the y-coordinates, okay? The difference of the y-coordinates, in this case, f of x minus g of x, times the width of the rectangle, which is dx, okay? The width of the rectangle, which is dx. So the total area is equal to the sum of all of those elements as they range from x equals a to x equals b. And I want to point this out to you again. Notice it has this kind of form to it. Let me use a different color here. Notice it has the form of the top curve minus the bottom curve. Okay, so when you're trying to find the area between two curves, it's helpful to keep this in mind. Top curve minus the bottom curve. Okay, top curve minus the bottom curve.